So, this is cascade control, very common and gives significant performance in improvements over very affordable costs in most cases, and therefore, are widely used. Now, we look at some other control structures, namely selective override and split range control. So, first start with selective control. So, as we said that what we are doing here is that we are just what are we doing, the loop is standard, the only change comes here. So, what we have shown here is that the same sensor, actually we have shown that as if the same sensor values are being the same process values are being fed, but actually that is not so. This means that the same process variable, for example, room temperature, are being sensed by 3 different sensors which are at 3 different locations. So, therefore, although they are being tapped from here, so these signals are not identical, but they will be similar. And then here we have some selection or basically signal processing scheme. So, we can what signal processing scheme we will apply depends on what we want to achieve. So, for example, if you want to achieve an overall temperature of this room, so then we should, and some sort of an average, then we should take an average value. This process should not select, but rather take average. If you want to know, if you want to ensure that in no corner of the room the temperature will be more than 25 degree centigrade, then we should take the highest temperature of these 3 and try to control that. So, temperature at every point of the room will be more than the set temp or will be less than the set temperature. So, in case of room cooling that is the case. So, in that case we can choose the maximum value, right. There are even other applications. For example, sometimes there are very catastrophic effects can occur in feedback control loops if one of the sensors fail. So, you can imagine that if there was a single sensor feedback and if the sensor failed, some wire torn or something got burnt out or some electronic circuit problem, immediately suppose that this signal goes to 0 due to failure, then what will happen? This will the controller will have no way of knowing it, and it will simply see an error, and therefore, it will try to drive the process unnecessarily, but that driving will not improve this value, because it is due to a failure, it is not sensing anymore. So, in such cases industrial accidents may result, equipment may get damaged. So, what people often do is that they take S1, S2, they will put 3 sensors suppose to sense the same variable, and then they will put a voting logic. That is, if all 3 of the sensors are working, are normal, they have not failed, then their readings are going to be very close. If any one of the sensor readings goes significantly away, so 2 of the sensor readings are here while the third one is here, means that the third one could be faulty. So, in which case the third one's value will not be used in control. So, it will be cut out and only the average of these 2 will be used. This is called triple sensor voting, and often applied in various critical control loops. So, by doing this you can achieve a certain degree of sensor fault tolerance. So, in such situations you can use sensor selective control. There are even other situations where basically where you can do median filtering, that is you can select outliers. When if suddenly one sensor gets a big piece of noise, then if you choose always the middle value, then you can reject noise better. So, you can also use it for doing various kinds of filtering. So, so selection of feedback for either minimal maximum values or mean values or median or mode values. So, depending on various applications you could choose. This is selective control, very common sense approach, but can sometimes give you significant protection from things like failures. Coming to override control. In override control, what we are I mean the same system could be operated based on two different modes or philosophies. So, they are basically it is something like an if then else logic, that if as long as this is happening, operate the system in this way, but if that happens, operate it that way. So, essentially this control loop is a sort of a supervisory structure which switches between, in this case it will switch between two sensors to drive the same actuator, and which sensor it will be used depend on which mode it wants to operate the system in. So, typical example, as a common sense example, here you have something like a boiler where you are getting feed water and you are having heat input. So, you are producing, let us say, steam. So, so what happens is that you are producing steam, you have water, and so there is a water level and steam is going out and being used for some purpose, maybe it's a steam plant for the whole factory where steam is required for several other purposes, for heating up certain things. So, what you want is that you want you don't want this level to fall to too low levels. So, if it falls to very low levels, then immediately it is a level loop which should get preference. On the other hand, if this if the pressure the pressure of the steam should not go beyond a certain limit, because then that may cause leaks, that may cause accidents. So, if the pressure goes up to over a certain limit, then the pressure control mechanism should take precedence. So, you are having two different control loops, and which one will take precedence in a given situation, that depends on the state of two variables. So, that is happening because it is like a protective scheme essentially, because the controls will be actually, so it coordinates, because how much of steam will be finally drawn here, that is also not within the purview of this controller. Similarly, how much of feed water is going to be fed in, that is not also within the purview of this controller. So, what happens is that if this level is falls too low, then what will happen is that the judicious strategy will be to close this valve, so that steam is not going out. So, what it will cause is that the level will rise. So, we will not draw steam from here, and similarly if the pressure goes too high, then also we should close the valve, because otherwise it will so the pressure will be controlled. So, depending on these two modes, so closing the valve means a lower input, opening the valve means higher input. So, whichever one needs to close the valve, that one will be used. So, this is in one situation one control strategy will override over the other. So, that is why it is called an override control. So, very simple, and essentially this is a supervisory control, I should say, because this is more like supervising the process and changing the configuration of the process. So, coming back to the next one, the last one, that is split range control. The first example is of heating, ventilation, air conditioning. So, we have the standard, this is the space that we want to control, there is a temperature transmitter and there is a temperature controller, and we also have a set temperature which we generally set using a dial or sometimes using remotes nowadays. And the temperature is affected either by hot water, if you in countries abroad for heating rooms, they have heat exchangers installed in rooms, various corners of the room, and through which they send hot water, or you can have cold air as in air conditioning. And depending on whether you want to heat the room or cool the room, that is depending on the set temperature, which whether it is greater than ambient or less than ambient, you have to either activate this actuator or activate this actuator. So, this is so on some range of error. So, some range of the set temperature. So, when the set temperature is greater than the ambient temperature, in that range you use this actuator, there is a hot water actuator, and when the set temperature is below the ambient temperature, in that range you use the cold air actuator. So, this is why it is called a split range control, because the range is split into two different control modes. So, so you see that typically speaking, this is the ambient temperature point, this is the ambient temperature point, and if the set temperature is above it, then as the error increases, the hot water valve gradually gets opened. So, the control input, that is the overall control input to the process, which changes its temperature, in this temperature range it will gradually rise and then finally will become stable. Similarly, when the set temperature is below ambient temperature, then the cold water valve characteristic will be followed and that will rise. So, the overall control input characteristic is like this over the two ranges, and in this range you operate the cold water valve, and in this range you operate the hot water valve. So, this is the standard HVAC control of spaces. Here is another example which is for a reactor, which is very similar. So, here what you do is the reactor, you want to control the pressure in the reactor. So, the pressure in the reactor could be either caused by controlling the feed rate or by controlling the product outflow rate, right. So, in the initial part of pressure, you control you gradually open the product valve. So, you see this is the product valve characteristic. After some time the product valve is fully open, so it cannot be, so the pressure is increasing. So, you gradually open the product valve. Now, if after this point the pressure cannot be affected by the product valve, because the product valve is fully closed. So, in that situation you start closing the feed valve. So, the feed valve is operated here. So, actually your true operating characteristic is this time you open product valve and this time you close feed valve. So, this is split range control, where you have only one sensor, but many actuators. So, we have come to the end of the lecture, and just want to have some concluding remarks. Firstly, on this multi-sensor, multi-actuator control, which is processes often need supervisory control logic. So, you see that you, apart from your basic control logic, which is there in the either in the hot water valve or in the cold water valve, there will be an automatic controller. But even above that, you need some logic based on again process variables, which will ensure which one will be working, which sensor will be active, which actuator will be active, which controller will be active. So, this is called supervisory control logic, and for process operations you often need that. So, this is sometimes achieved by these control loops. So, you can switch among operational modes, and these supervisory control logic schedules sensors, actuators, connects, sometimes use this actuator, sometimes use that actuator. So, based on operating points and set points. And only one thing is that when you must ensure that when you are switching from one mode to another, too much bumps we have considered bumpless transfers in the context of PID control. So, we should not have too many bumps when you are transferring the from one mode to another, because that sometimes is not good for actuators or plants. So, that brings us to the end of the process control module. From the next lesson we will enter a different module of sequence control. So, what did we learn in this module? Industrial, just some concluding remarks, that industrial processes sometimes have very complex dynamics. They have phase lag, they have non-linearity, gains will change, but so that creates complexity, but at the same time the process dynamics is slow. So, sometimes it is good in the sense that fast processes are difficult to control, but at the same time sometimes disturbances also travel slow and they should be detected early, otherwise the large errors may persist for unacceptably long times. So, one has to take care of sensor and actuator nonlinearities. One of the major actuators called flow valves have significant nonlinearities. Several sensors like temperature sensors, flow sensors also have nonlinearities. So, they should be taken into account. And typically in, I think, around 90% of the cases PID controllers are used, sometimes with various special configurations for anti wind up, for bumpless transfer, etc., as we have seen, for special structure for feeding back derivatives, but generally the controllers are PID. They are very extremely common, and PID controllers have to be tuned. Control tuning can have significant impact on controllers, and there are various, for example, modern day controllers come with very quite sophisticated features of tuning software. So, tuning is very much required, and you also need sometimes some supervisory logic to improve performance, prevent failures, carry out diagnostics. So, all these are also necessary. Similarly, supervisory logic may also be used to treat interaction between multiple control loops. And finally, often for getting the best results, often various kinds of special control structures have to be used, but the good thing is that with years of experience, for most of the common industrial processes very well known solutions exist. So, one need not worry too much. So, that brings us to the end of the process control module. From the next lesson we shall take up sequence control, and coming to a lesson review, we have seen problems of single sensor control, cascade control, and multi sensor multi actuator control in the form of selective override and split range. Points to ponder: give so you mentioned what for what kind of processes cascade control is likely to be effective. So, take some examples and examine how the two subsystems should be such that process control is effective. Why higher stability margin leads to improved transient response, that is why that you can try to explain. It is related to basically related to the range of controller gains that you can have, and draw the block diagram of a cascade control loop for a practical industrial process. This is very important, and one should be able to draw it. Similarly, block diagrams of selective control loops and override and split range control loops are useful exercises to be done. So, thank you very much.